Well, thank you very much. It's a pleasure to be here. This is my second time in my life I've visited Germany. I'm having a great, the city is beautiful and enjoying it. I want to thank the organizers for giving me this opportunity to speak to you about something very near and dear to my heart. I like to begin my presentations with a disclaimer, and my disclaimer is that I don't claim any gifted insight. I don't claim to have the answers to the world's problems. I am me. I've lived my life just like you've lived your life, and I've come to see things in a particular way. And so when I say we should do this, please understand I'm not so presumptuous that I feel I have the right to tell other people what they should do. I just want to share my thoughts, and if some of my thoughts make sense, that's great. If they don't, that's okay too. You know, I've had a strange life. In my fourth decade of being a professional chemist, the first 10 years of my life, I was an industrial chemist working at Polaroid, doing chemistry at the bench. And then for the next decade of my life, I was an academic. I was a professor at the UMass system in chemistry, plastics engineering, and biochemistry. And then for the last 10 years of my life, I've had a startup company called the Warner Babcock Institute, which is an entrepreneurial small company. And over the last 30 years, I've found myself being involved in chemicals policy, either in California as the Chemicals Policy Initiative, or in Washington, D.C. with TSCA reform, or working with REACH legislation and other things. So as a practicing bench chemist, I've found the opportunity to see how chemicals are managed. And so I'm at a point where I've had this view of how we do chemistry, how we teach chemistry, how we invent chemistry, and how we've managed chemistry. And really, to get to a sustainable trajectory, there's things that need to change in all aspects of the chemical enterprises, not in just little isolated places. I can't believe it's been more than 20 years that we've been doing green chemistry. It's actually been much more than 20 years. You know, the United States started their Presidential Green Chemistry Challenge Award back in 1996. So it's now survived the Clinton administration, the Bush administration, the Obama administration, and we'll see how long the present administration. And so that in and of itself is quite amazing, you know. And of course, you know, Xavier has the program and the awards program and the Crystal Faraday program in the UK, and there are many other programs that have emerged over the decades in green chemistry. You know, and then from an academic perspective, I realized there are things happening all over the world. In North America, where, as you can tell by my accent, I'm from the Boston area in Massachusetts, we have the Beyond Benign, which is promoting the green chemistry commitment, where over 50 universities have actually signed on to try to find some way to get green chemistry in the mandatory curriculum, not as an elective, but as a fundamental part of teaching chemical sciences. Organizations around the world, we've got ISC3, we've got at the Technical University in Berlin here, the Chemical Invention Factory, there's the center at Berkeley, there's in Monash in Australia, there's the Green Chemistry Futures, and then as I mentioned, there's Beyond Benign, and there are dozens and dozens of other universities worldwide now that are dedicated to green chemistry. And it's just breathtaking to see what's happening. So what I did yesterday is I went up into my hotel room and I did a SciFinder search of the keyword green chemistry in chemicals publications. And you can see an interesting trajectory here. You know, way back in 1991, there started to be one or two publications every once in a while. And then Paul and I, we wrote that book in '98, and you can see the trajectory. What I'm most excited about, though, is, you know, you've got blue as the academic publications, but green triangles here are actual patents, intellectual property that is embracing the concepts of green chemistry. And it says that this is simultaneously a profoundly difficult intellectual pursuit of the chemical sciences, but it's also a very practical pursuit from an industrial perspective. And you've got these business analyses. Pike Research did this analysis a few years ago predicting that green chemistry would be a $100 billion industry by 2020. From what I understand, it's already passed those numbers. So there's an interesting response that society is having to green chemistry. But where did the principles actually originally come from? I think it's useful today to just kind of reflect where did that happen. So as I mentioned, my first 10 years of life, I worked at the Polaroid Corporation. And I was blessed. I worked in exploratory research and got to do a lot of different technologies, holography, medical diagnostics, all different things. And my formal training, my PhD at Princeton was in medicinal chemistry, organic chemistry. So working at Polaroid, I learned a lot about polymers and material science and all that, but I approached it from an interesting perspective. I looked at how nature controls molecules and how, we humans, we tend to synthesize these very complicated molecules. I consider myself a synthetic organic chemist, but what do? We do the propyl, butyl, futyl. We just keep making molecules to try to get just the right molecules that we can make. Nature uses mixtures of molecules. And what I started doing at Polaroid is filed the first patent was filed in '91. Looking at binary systems, constructing phase diagrams of multimolecular organic systems, taking the crystal structures and correlating the crystal structures geometrically to dissolution kinetics, to redox properties, to the things that we would traditionally try to control with covalent chemistry, I tried to control with non-covalent chemistry, and I called it non-covalent derivatization. I'm so tied up with this stuff. The license plate of my car is NCD, so I could go on and on and on, but I'll spare you this. But at Polaroid, interestingly enough, one of my inventions, they actually called them Warner complexes, went to large-scale manufacturing. And in the United States, you need to get EPA approval to go to large-scale manufacturing. There's these documents, it's all covered by TSCA, these things called low-volume exemptions, pre-manufacturing notifications. This is back before the internet, so we filled these bankers' boxes and sent them to Washington, D.C., and we waited, and the EPA was having trouble approving the technology. Not because of toxicity, not because of the environment, it was just so new, so different. They never heard of non-covalent derivatization. They said, oh, small particles, are you crazy? Molecular complexes, are you high? They didn't know what I was talking about. And so Polaroid stuck me on an airplane and sent me to Washington, D.C. to go and talk to the EPA about non-covalent derivatization. So I got a bag of overhead transparencies. I'm at the door of the EPA building. I'm a little scared, a little bit mad. I'm going to go talk to these people. And I meet Paul Anastas, the branch chief of the Office of Pollution Prevention and Toxics. Now, I say I met him. No, I've known him since the beginning of time. He and I grew up together in the same city. Known him since we were 15 years old. In fact, went to the same university undergraduate. At that point, I was playing in a jazz band with his older brother. There's his older brother, Nick, on the sax. There's me on the keyboard, my older brother. And this guy here playing guitar, if you've ever been to Las Vegas, the person who plays Rod Stewart for Legends of Rock is him. Has nothing to do with this talk, but I thought it was cool to tell you. So anyways, I was at the EPA, and I'm saying, gee, we used to have this process where we were making these very complicated molecules, several step synthesis, all these reagents and things. Here we have this non-toxic, environmentally benign, aqueous process, and the EPA is having a difficult time because it's different. Isn't anything better for the environment, anything better for human health going to be different? If the EPA has within it mechanisms to make it hard to do different things, isn't that the opposite of what they should be doing? Shouldn't they be promoting that which is good? Obviously, industry gets it, right? You've got a hazardous material, you've got a safe material. If you tally up the costs, the storage, the transportation, treatment, disposal, regulatory, liability, work health and safety, on and on and on and on, it costs a lot of money to work with hazardous materials. I would argue that the single biggest impediment to success in the commercial landscape isn't the technology, isn't market awareness, it's understanding the restrictions imposed by various regulations on how you can manufacture things and your responsibilities when you do. All right, and so I went and we tallied all the environmental regulations just in the United States, all the way back to 1870. Not a whole lot happened, all right? And then in 1962, Rachel Carson publishes Silent Spring. It's the year I was born, and all of a sudden, you see a change. Okay, all these dots, all these acronyms are pieces of federal legislation saying if you're working with this, that, or the other thing, you gotta make sure it's not getting into the land, the air, or the sea. Obviously, there's a trend here. A statistic that's really interesting is DuPont, several years ago, DuPont's research and development budget was $1 billion a year. Same year, their environmental compliance budget was $1 billion a year. They were spending the same amount of money, this is typical for most companies, spending the same amount of money inventing their future as they were maintaining compliance with regulations and things like that. So the CEOs say, from now on, I want all my scientists to only invent non-toxic, environmentally benign, unregulated technologies. Thank you very much. It would just make sense if they were already safe in the first place. But do we train scientists to be able to do this? Interestingly enough, in the United States, definitely worldwide for the most part, with few exceptions, no university requires a student in chemistry to demonstrate any knowledge of toxicity or environmental impacts. If you think of your programs, in Germany there are a lot of universities that do have such programs, but worldwide, most chemistry programs never learn anything about mechanistic toxicology. So how are we going to invent safe, sustainable technologies if it's not part of who we are? And so Paul and I, we realized that there needed to be a science. There needed to be a thing where people could meet, could talk. We needed to have journals. We needed to have textbooks. We needed to have classes. We needed to have conferences and workshops. And that's the birth of the book, Green Chemistry Theory and Practice. A guy in industry and a guy at the EPA realizing that we needed to create a mechanistic chemical science so that people could share best practices and start to make advances on things that are safe and sustainable for society at the chemistry level. Now, I'm always shocked. Had I thought anyone was ever going to read this book, we would have written a better book. But it was at the right time, at the right place. But if you open the book and you turn the pages, you just kind of say, yeah, that's obvious. Yeah, that makes sense. Yeah, that's obvious. It's like, anyone could have written the book, okay? It's just a very common sense, but for some strange reason, the field of chemistry just never did. All right, and so I feel stunned. The book has been translated to over 15 languages. I've been to over 50 countries, meeting presidents and prime ministers and princes and cutting ribbons and giving talks about this thing that any chemist could have written. Okay, there's nothing earth-shaking, it's just logic. All right? But what I'm most proud of course, is the 12 principles of green chemistry that speak to the designer at the moment they start inventing chemistry. That's when they need to be thinking about the real-world implications. Not after it's already invented, heaven forbid, not after it's on the market, but the moment you start thinking about it, it's kind of like an intellectual checklist of things you may or may not be able to do in the current state of science. All right? But to me, green chemistry is the act of removing hazard from society. Not the discussion, not the philosophy, but the act. It has to happen. And so, yes, green chemistry has to have a technology that's better from an environmental perspective than some incumbent technology. But that's not enough. It has to have superior performance. If it doesn't really work, who's going to use it? And it has to have appropriate cost. If it's too expensive, a lot of social issues around that. And again, who's going to eat it? So really, for something to be successfully implemented as green chemistry, you have to have superior performance, superior cost, and oh, by the way, here's the sustainability narrative. And so when someone comes to me and says, oh, John, we have to go beyond green chemistry, we have to worry about performance and cost, they didn't read the book. Because the whole point is that this is pragmatic. And what we can't do, now there are hazardous materials that we must be dependent on government policy to protect us from. And we will always need government policies to be vigilant in looking at the hazards that we expose ourselves. So bans and policies will always be necessary. But in a hypothetical world where an election could happen in the United States and all environmental regulations all of a sudden start going away, that's not sustainable. But if the technologies are invented to work better and cost better, then it becomes impervious to the alterations of government. And in the long run, it will be more sustainable. So at the end of the day, this is about invention. This is about entrepreneurship. This is about bringing technologies to society. And in my opinion, if you accept my definition that green chemistry must have superior performance, superior cost, and oh, by the way, here's the environmental benefit, the biggest barrier to its adoption is its invention. And now, never in history did an incumbent product lie down and say, take me, I'm yours, okay? The world has a way of fighting new innovations, okay? We were making vacuum tubes decades after the transistor was invented. People have a vested interest in what they sell. So just because it's green, it's not going to give us, unfortunately, any benefit in the market. Okay, we're going to have to fight market trends, we're going to have to make something better, and we're going to have to make something more cost-effective to truly do this in a sustainable way. I wish the world was different, but it isn't. So at the end of the day, this makes it a chemistry problem. Now, I want to say that over and over again, because in sustainability, this work for many, many people, not just chemists. But we chemists have a skill set to make molecules do things that they want to do. That's our world. And so we need to approach sustainability as chemists doing chemistry. All right? And so after 10 years of Polaroid, I went to the academia and started the world's first PhD program in green chemistry. Everything that's in a typical chemistry program, but added a one-semester class in mechanistic toxicology, added a one-semester class in environmental mechanisms, added a one-semester class in law and policy. Over the next 11 years, about 120 students passed through this program at various levels. The average time it took one of these students to get a job in industry, 2 days. The longest any student spent looking for a job was 6 days because she turned down her first several job offers. Industry gets it. You mean you've got a world-class chemist that knows how to invent and solve problems, but also has some understanding of regulations, of toxicology. It's an unmet need in industry, okay? Because of all the products and processes that we have available to us, the ceiling tiles, the carpets, the electronics, the textiles, I would argue maybe 10% escape someone's scrutiny. 90% of all the things that we have in society today got somebody a little bit anxious. Now, sometimes they're very serious problems, and sometimes not so much. And we're in a society where perception and science kind of struggle with each other. That's a different issue. But we have this. Maybe 90% of the problems need something different. If you do an alternatives assessment, there is a moral and ethical responsibility that someone does an alternative assessment and searches in the supply chain for alternatives. I would argue maybe you'll be successful 25% of the time. But today in 2018, I would argue 65% of the technologies or more haven't been invented yet. What better time in history to be a chemist, to be in material science? You know, you ask the general public, what's the problem in sustainability? And it's as if the chemists are the cause of all the problems. Well, how do we solve the problems without chemistry? Why is it if a 10-year-old child is dreaming of growing up and saving the world, whatever that means to them, and they list the careers that they're going to go into, is chemistry on the top of that list? What are we doing wrong in how we sell our profession that we're the problem and not acknowledged as the very solution? Can you imagine an undergraduate student working in a lab, pouring beakers and flasks, could invent a technology that hundreds of thousands of people they will never meet will avoid being exposed to some hazardous material because of their work? What could be more empowering? What could be more intellectually challenging than that? That is the stakes that we have facing at us in the chemical enterprises. Because where do products come from? We take molecules, we turn them into materials, we call that basic research. Materials into components, we call that applied research. Components into devices, we call that development, and when we do a lot of it, we call it manufacturing. Well, if you're in the business of manufacturing a product, you worry about its performance, you worry about its cost, you worry about, hey, wasn't that my definition of green chemistry? There's nothing new here. It's the way business has always been doing business. It's just now we've got to look at the environment. We got to ask, where did those molecules come from? At the end of a product's life, where do they go? When we manufacture it, when we sell it, when we use it, who is the only person who can change the equation? The inventor. After it's invented, after it's being developed, after it's being manufactured, you're done. And so the opportunity to make change isn't at the end, it's at the beginning. The moment he or she puts that pencil to paper and starts thinking about what they're about to design, we need them to have the tools then. Afterwards, too late. All right? So how does green chemistry fit into the big picture of sustainability? You know, people like words and definitions, and again, I remind you of my disclaimer at the beginning. This is the way I look at the world. The way I look at the world is sustainability covers everything that humans do. We could talk about sustainable economics, sustainable agriculture, sustainable education, business, engineering, chemistry. There's a million different ways that we can cut that up. Sustainable chemistry is the components that talk about materials and molecules. We got to worry about policy, we got to worry about remediation, we got to worry about exposure controls, alternative energy, water purification, green chemistry, and other things. I see green chemistry as a subset of sustainable chemistry because it is the part, green chemistry is, that does not look at the application. It does not go down the route of the ends justifies the means. It says, what is it made of? What are the materials that constitute this product, independent of what the product does? So what are the solvents that we use? What are the catalysts? What are the feedstocks? What's the toxicity? What's the persistence? Hey, I get 12 principles, why don't we just do it that way? And it's looking at the building blocks that designers make products of, but it's what the chemists do. Okay, and so if you think of it from a life cycle assessment, what I did was I took all of the 12 principles and I spread them out from molecule to product. And you look and you see all of the principles cover different aspects of the life cycle all around the place. And if you're in marketing, you kind of scratch your head and you go, oh, this sounds weird. I don't know how I'm going to do green chemistry. It's not really a marketing thing, all right? But if you're in R&D, that's where it is. So green chemistry is not an assessment tool. It is the verb of how to improve the assessment. So you do an assessment of a technology by whatever method you want. You then employ green chemistry to improve it. And then you do another assessment to validate that you actually made that improvement. So it's all a collaborative hand-in-hand thing, but green chemistry is the act of improving the technology, not measuring it. Those are tools that green chemistry must have, but it is the invention that it's all about. This isn't the birth of ethics. Chemists who never heard of green chemistry, of course they care about human health and the environment. We always have. But it's interesting. The way we have approached it for over a century is essentially chemistry has to be toxic. It's just the way it is. But it's okay because we wear gloves to protect our skin. We wear masks to protect our lungs. We put goggles on to protect our eyes. We install scrubbers and filters and smokestacks to protect the air, the land, and the sea. We got it all covered. Two things. One, all of these cost money. If an organization is going to protect the environment and human health by doing this, it is an added cost. But the other problem is, every once in a while, these fail. And when there's a disaster that we hear about, it wasn't that it was not attempted to be protecting the environment and humans from, it's something went wrong. And so if green chemistry is a revolution, it's saying we will always be dependent on mitigating exposure. If we want to protect risk, if we want to deal with risk, mitigating exposure is something we're always going to have to do. But if the mechanistic chemists get in the lab and look at the structure and learn from the fields of toxicology and environmental health sciences and reduce the intrinsic hazard, all of a sudden the exposure control becomes easier, and all of a sudden we're talking about environmental protection as a way of profit as opposed to a way of cost. All of a sudden things look different. Using the skills of green chemistry and the innovative mind of the molecular chemist to design the material that is intrinsically less hazardous in the first place is easy conceptually, but very hard to do at the molecular level. All right? So I look at the world as a toolbox, okay? We have a toolbox with all different kinds of transformations. We have carbon-carbon bond-forming reactions, oxidations, reductions, hydroxylations, polymer syntheses. If you can design a material, you can probably make it. But if you imagine a green chemistry toolbox, where those same transformations are environmentally benign, non-toxic, non-regulated, like I said, this toolbox is 90% empty. I believe an individual, a company, a developing nation will open the green chemistry toolbox first. Better performance, better cost, and oh, by the way, better for the environment. Of course they're going to look in there. But odds are the draw's going to be empty. Then what do? Well, they say, we can't invent on a whim. You know, some people think you can create a Gantt chart and put invention on a Gantt. Next Tuesday at 2:30, we'll invent this. It's not the way chemistry works. It's the way invention works. You know, we try and we try and try. And so what do organizations that are facing the 21st century timelines of the economy? They shut the traditional drawer, open up they shut the green chemistry drawer, they open up the traditional drawer, they go, okay, what is it going to cost for the gloves, for the lawyers, for this, that? And they factor it into the cost, and they have to do that because they have to meet their timelines. So our opportunity is to make sure in the future, when people open these drawers, there's something there. And I feel that the biggest force in our society to do that is the startup economy. Okay, because they're not burdened with the massive infrastructure of big companies. They're not burdened with the infrastructure of academia. They can be agile. They can be responsive. And if they're focused on the needs, this is where it's going to happen. And this is why I'm so happy to be here talking in a session dedicated to startups, because entrepreneurship is a necessary component to the sustainability of society. All right, so 10, 11 years ago, I had the pleasure of meeting Jim Babcock, and he is my business partner, investor, and we started the Warner Babcock Institute for Green Chemistry. It is a dream come true facility a little bit north of Boston. It's a 42,000 square foot, that's about 4,000 square meter laboratory with everything you can possibly imagine to make small molecules, to make polymers, to fabricate devices, to extrude plastics, and then to analyze them, just everything under one roof. And we're just lucky to have these resources, but of course it's the people that make it work. Amazing people that are scientists that are dedicated full-time employees. It's a for-profit company that is working to invent things from an entrepreneurial spirit. Okay, and the way I look at it, all right, if you think about science, what is the scientific method? The scientific method is when we look at a phenomenon, we poke at the phenomenon and we hope that we're right in our prediction. And if we are, we pat ourselves on the head and think we have a theory that's going to stay. Interestingly enough, what do we do in business? In business, we have a product, and we have a market. We poke the product, and if the market responds the way we predict, we pat ourselves on the head, and we say, gee whiz, aren't we right? The problem we have is the world is full of what we call technology incubators, where they tape some technology and they try to commercialize it. And the problem is more often than not, that technology is very strong on science, but very weak on business. And so although massive amounts of money becomes available, it fails oftentimes because of the absence of green chemistry or other business things. And so what the Warner Babcock Institute is, we call ourselves not an incubator, but a technology greenhouse. And we focus on idea to prototype. And we put an equal balance of business and science into it. And if you're in a small startup, you've got to do this. You've got to anticipate the market needs. You've got to anticipate the business needs just as much as you're in love with the wonderful chemistry you're doing. You've got to always have that pull from the market. And if you can do that, then you can become much more successful. Right now, incubators, we accept a less than 10% success rate on an incubated technology, not because the people aren't great at what they do, but because the prototypes are missing important components. And we need to, as we become entrepreneurs and we think about this, really the concept of the technology greenhouse, I urge people to think about. So the Warner Babcock Institute is just a crazy, almost very difficult to explain situation. Much of our work is contract invention. 70–80% of our business is business to business, working with large multinationals. I call it contract invention. The company pays us to invent something for them. Okay, and then we have some government grants that we're doing some work with, but much of what we do, Cthulhu Ventures is Jim Babcock's investment firm, and we do our own invention where we've got an idea in our heads, and we start developing it, and we either license the invention to other companies to start up, or we spin out our own companies. And so we have spin-out companies in material science, we have spin-out companies in pharmaceuticals, and it's just kind of looking at the common stream in all of this is not the application, but the mechanistic chemistry. So I'm going to run through a couple examples to see what an entrepreneurial approach to invention in the green chemistry space could be. We've got several pharmaceuticals. We've got ALS, Alzheimer's, oncology, diabetes. One of the ALS drug, Parkinson ALS drugs, is actually in clinical trials where we've increased the bioavailability of a material, and in Australia it's in clinical trials. We're pretty excited that that's moving. We have construction technology. In fact, in the lab, in the institute, the same person working on the asphalt may very well be working on construction. In the United States, there's 1 billion miles of asphalt pavement. The sun and the air oxidize it over time, making it hard and brittle, so that every year about 10% must be repaved. When we repave it, unfortunately, it's so brittle and hard, it goes to a landfill. It's not reused. Maybe 5–10% is reused. So I said, gee, there's got to be a way to come up with an additive to use this oxidized stuff. So on November 25th, 2013, we dug up my driveway. Okay, my family wasn't happy. It was a perfectly good driveway. And these workers came with big trucks full of asphalt, and they were laughing at me. They were saying, John, you idiot, it's -8 degrees centigrade. You're using over 70% recycled material. Impossible. We're going to open up this truck, and a big hockey puck's going to fall on you. You're like, oh. So I go, okay. They open it up. It comes out like sand. They scream like school children. Here it is just a couple weeks ago. Beautiful. It works well, so you can use the recycled material. It lowers the processing temperature. It was so fast that we spun out a company called Collaborative Aggregates, and the product is called Delta S, and it's on sale worldwide now. And from idea in our head to starting the company was about 14 months. Okay, we have, you've heard about OSB lumber and building materials. You've heard that formaldehyde and MDI is becoming a problem, very famous cases of the off-gassing. So we've been developing a technology, we've done a multi-ton pilot scale run of a wood composite adhesive for OSB and other types of composite woods that outperform industry standard in performance at the same cost. Not a drop of formaldehyde, not a drop of MDI. It's pretty interesting, kind of excited. We have a hair color technology. We're contemplating the process of insect sclerotization, how a bug changes its exoskeleton over time. It goes from white to black. Well, gee, there's something in nature that goes white to black. People color their hair. This men's hair product uses as its key ingredient lead tetraacetate. You can't have a house with lead paint, but you can pour it on your head. And so I looked at it, and it's a terracinase oxidative cascade. So I didn't grind up bugs. I mimicked this oxidative cascade, put it in a beak. It was a seed extract, ground it up, got some gray hair from a vendor, and it worked. The problem was it was dark, it was light, it was all over the place. So I called the vendor and said, "Oh, John, that's not one person's hair. It's a bunch of..." And I realized what we had done is we didn't come up with a hair coloring system. It restores the human pigment. If you've seen my pictures, you must be very confused who John Warner is, because I look very different from picture to picture. This is me 6 weeks ago. I had to go to a meeting where I had to show I'm not only but that's the color my hair was 30 years ago. If someone had black hair and it's gone gray, it goes black. If someone has brown hair and it's gone gray, it's gone brown. It restores the human pigment from all edible food contact materials. So just like your finger has a fingerprint, your hair has a hairprint, and you really can't tell. And so we didn't start a company. We licensed it to Paul Hawken, who started a company called Hairprint, and that's been on sale now for almost 3 years. If you go on the internet, myhairprint.com for $39.99, right now they might throw in a knife. Okay, so it's an interesting green chemistry technology. I found myself on the General Assembly of the United Nations a couple years ago. 14 days earlier, this cable TV show, Whale Wars, called me up and said, "Oh, John, we have 75 tons of this illegal fishing net." And they were working with an organization called Parlay. They sent some of the material to us at Warner Babcock. We had to separate the nylon from the polypropylene, do a bunch of different things to it. They needed it extruded to a specific size. We didn't have an extruder. We found plans on the internet, so we built the extruder and sent it to Adidas. And standing beside me on the center stage of the United Nations General Assembly was a guy from the board of directors of Adidas holding up their 2016 running shoe made out of ocean plastics. That was done at Warner Babcock in 14 days. All right. We have an electronics recycling technology where we take lemon oil, we hydrolyze the limonene to a 50% ratio, probe sonicate, disperse it in water, grind up lithium cobalt batteries, and can recover 100% of the lithium cobalt batteries using an aqueous oil extract from fruits as the process. We've got some pilots going on around the world. We have a biofiltration system that's funded by DARPA, where we're directly making photolithographic semiconductors of TiO2 by direct lithography. We're spinning out this week a solar company. We've got a dye-sensitized solar cell company that we're very excited with on ambient light technology. We have water harvesting technology, polymers that essentially under one condition are hydrophobic, another condition are hydrophilic, switched by light. So imagine, this is an oversimplification, but imagine a rowboat on the ocean. You've got this polymer on the underside of an umbrella. When the sun comes up, it becomes hydrophilic and water absorbs on the film. When the sun goes down and becomes dark, it rains pure water in the rowboat. Now this is an oversimplification. We have it going passively with a diurnal cycle, but we also have it happen in a millisecond in the shadow of a windmill to capture and release water using these photoresponsive polymers. We've got a Bpa-Free can lining system. The point here is everything that I've just described to you, was done using 20% of our resources of about a 25-person company over 4 years. Okay, think about all of those technologies I just described to you were done using 20% of the resources of about 25 people over 4 years. People say, oh, we're too busy to do green chemistry. Oh, we got to go fast. I don't feel we're going so slow. All right? And the thing is we're not any smarter, any better, any more creative than any other group of chemists. It's interesting enough that society, we live in constraints. To believe we don't live in constraints is a mistake. We are successful not in spite of green chemistry, but I'd argue because of it. And here's the thing. All of us chemists are taking the same classes, reading the same journals, going to the same conferences, doing the same thing. If you said to a group of scientists, from now on, you can never use the letter D. Any molecule that starts with the letter D, you can't use. That would be kind of silly. But just that restriction, the scientists would have to think differently. They'd say, oh, I can't use a molecule. And surprisingly, you'd find them more innovative. You'd find them more creative. But wait a minute, the letter D is silly. How about green chemistry? Because not only will you be more innovative, but your time to market will be faster because you've already anticipated implications on human health and the environment and regulation. So I'm so proud to be asked to come and speak here. I think that this conference is a testament to the creativity of all the people that are doing amazing things. It's just amazing to walk around and look at the posters and see what everybody's doing. I am so happy my website is johnwarner.org. Trying to get FDA approval for this for a cure for insomnia. If you click that link and you're still awake in 4 minutes, I'll be surprised. But if anything caught your attention, there's more description of it there, and of course the Warner Babcock Institute. I'll be here today and tomorrow. So I thank you for your attention, and I congratulate everyone in this room for making green chemistry what it has become. And I am just humbled and amazed by what you guys do. Thank you.